Let's take a look at a very special situation that's associated with thin wall pressure vessels. It's a big picture thing and it is a big deal in all kinds of ways. And that is, let's take a closer, more realistic look at what's happening to the system, right? This only applies to the cylindrical vessel, and that's because the hoop stress and the longitudinal stresses are not the same. The hoop being twice as big as the longitudinal. And that's what you see with more circle down here. The little one to the right is the in plane, or in the plane of the wall of the cross section, or in the plane of the wall of the vessel. And there you've got that hoop stress PR over T, the longitudinal one PR over 2T. Remember, that's R in this case instead of being the diameter. Right now, if you were to look not at that in plane, but rather recognize that on the outer surface, you have zero normal stress, right? So if you were to take a little slice through the wall thickness and sort of look at it where you see this little longitudinal stress, but now you're looking down that barrel and you just see that little then square on that little surface, then you have a zero radial stress. That's the normal stress, and you have the hoop stress at PR over T, right? So that's here, and then that hoop stress all the way out here, that's a really large circle. That's one of the out of plane ones that you're dealing with. And so the normal stresses don't get bigger, but wait a minute, the max shear stress all of a sudden got much larger. Before, it was at about a PR over 4T, and now it's PR over 2T. It's twice as big. So if you have a material as ductile metals are that are sensitive and usually dictated by shear in their ultimate failing, you stretch it out, you actually have a max stress on the shear stress on the 45-degree plane, and that can be a critical one. It's actually failing in shear, even though it's a tensile kind of behavior. This can be, depending on the ratio of shear yield to tensile yield, that can be a pretty important number that's showing up. If you look in the other direction, sort of on this bottom surface, then you'll see the longitudinal stress being the maximum and the radial stress is still zero. So that's this other smaller circle. So that's just different sides of the stress cube that we're looking at that we see in the plane side. And then these other models that show up. So there's three more circles to be looking at. If you go to the inner surface, this gets also interesting because instead of that radial being then zero, it's now got a small value, relatively speaking, that's the internal pressure that's being pushed on that. In that case, this more circle gets even a little bit bigger than it was before. It's actually going to creep over into the compression side, and that will make, again, the shear stress a little bit larger yet. So that's a pretty interesting thing that's going on here. So it all comes down to then in the design of these cylindrical vessels at the material level, and that is, what's the ratio between the tensile maximum strengths and the yield strengths. For a lot of metals, that's about a 60% value, and you ultimately then tend to look at things from the tensile perspective because the yield is high enough that even with the kind of thing that you're seeing here, which the absolute maximum shear stress is twice or one half, that is, of the absolute maximum tensile stress. But if the yield strength and shear is 60% instead of 50%, it's even bigger, then you're going to be dominated by the tensile behavior, right? Study this little portion, go back and convince yourself of what's really happening in these more circles. Very powerful tool, but also a powerful impact about what's going on here, about where the true maximums are located.